redox titrations. In Chem 20, you mastered acid-base titrations, and you would have an acid as your titrant or a base as your titrant, and the other one as your sample. And because you have two colorless solutions, that when you add them together and you get colorless products, your acid and base, and yielding a salt and a water, there is no way of knowing when you have reached this perfect endpoint, this stoichiometrical ratio of 1:1. And so we have to use an indicator in there like phenolphthalein or bromoethanyl blue, which will change color to tell us, oh, we've just switched from being an acid into being a base. And there's that huge shoot up in our pH change. Remember those pH curves? So we don't have to usually add an indicator to redox titrations because they are often self-indicating. A lot of redox reactions involve transition metals. Transition metals have different colors when they have a different oxidation number. So, for example, copper 1+ oxide is black and copper 2+ is blue. And so as soon as you change the oxidation number on my transition metal, I get a very different colored compound. So I can often utilize that in my titrations, and I don't have to add an indicator, and I don't have to look for something else that changes color on me. So they are self-indicating. So here's a setup for you. You've got a burette and an Erlenmeyer flask, and the sample's in the Erlenmeyer flask, and I would have pipetted that sample in to get my 2 extra decimal points there. So I'll use my pipette, I take my sample, I get my sample into my Erlenmeyer flask, and this is a sample of tin 2+, and in my burette, which is where the titrant is, I have this purple permanganate solution. Now in my sample, I also have to acidify it so that in my species list, I have some H+, so the H+ can react with the purple potassium permanganate, and this becomes our very strong oxidizing agent. In fact, on your data booklet, it's right up there at the top left-hand corner of oxidizing agents. So I'm utilizing not only its color, but also its strength of oxidizing agent. Okay, so as I add a drop of this purple MnO4 2-, as soon as I add a drop of this, it finds a molecule, or not a molecule, a species, an ion of your tin 2+. They come together, they react, and they form the products. Because I've just reacted that drop that's hit the sample, it's disappeared, sort of. So the purpleness is gone, and it's become the colorless Mn2+. Mn2+ is colorless when it's really dilute. And of course, if I've only just formed 1 drop worth, it's very dilute. And so I've added my purple, I've made a drop of my product, which is colorless, and these are all colorless. And so what I see is still colorless. I add another drop, the other drop reacts with this whole flask full of tin 2+. That drop's purpleness also disappears, and I form again what I see as colorless. I add more purple, it reacts, colorless. I add more purple, it reacts, colorless. Until one day, all of the tin 2+ that are inside have also all reacted. So I reacted the tin 2+, each time I added a drop, and eventually all the tin 2+ is going to be reacted. Upon that time, I'm going to add 1 more drop of this purple potassium permanganate. When it hits the sample, it has nothing to react with, nothing. And so that purple drop then taints the color of the flask. And overall, that flask then changes color into no longer being colorless, but being 1 drop of purple within a sea of colorlessness. And so that becomes, well, a really light purple pink. We call it pink. So this would be an endpoint color of my colorless sample. So what I'm looking at is the sample would go from colorless to light pink because of that extra 1 drop of purple that can't react. And now I've reached my endpoint color, my stoichiometric ratio, and then I can do some stoichiometry. The other common one, besides the purple potassium permanganate, is my orange dichromate solution, if I use an orange dichromate solution, it's not as nice of an endpoint color because the purple to colorless is beautiful. This is orange to green, which, as you can imagine, it just like, it's kind of messy and kind of gross, but it works. It works. I add a drop of purple to orange, it reacts, but it forms greenness. So it's sort of hard to tell when that extra drop of orange is added and not reacted. But it is also, you can add some more stuff to it to make it look a little bit easier to read. So anyway, that's another common one that you will see in your questions. Speaking of questions, the first question in your notes package is quite lengthy. It says all of this. A student is standardizing. I'm going to highlight the Chem 20 words that I still expect you to know in Chem 30. A student is standardizing a sample. So the sample bit, it's in the flask. So if they ask me for the color that it would start at, I'm going to look at the color of the sodium thiosulfate and not the other one. So a sample of sodium thiosulfate solution using that of a standardized solution of acidified potassium iodate. So I know what acidified means in terms of my species list. An average of that much titrant, that's what's in the burette, is used to reach the end point. The end point is where I stop the titration because I've reached my perfect balanced equation stoichiometrically. Calculate the concentration of the sodium thiosulfate solution. And it gives me this skeletal reaction where it's obviously unbalanced. That's what the blanks mean. So therefore that leads me to understand I have to write a balanced redox reaction, which I'm going to have to use major OHE to do because these are not in your data booklet. And then I have to do the stoichiometry underneath. So I'm going to need some board space. Hold on. Okay, a quick reminder of major OHE then. So I can see that the IO3 minuses are going to be becoming I minuses. That's going to be half the story. And the other half of the story is the SO3 2 minuses must be becoming my S4 O6 2 minuses. So major species already balanced. O's are my balanced oxygens using water. So I have 3 oxygens on this side, so I needed 3 waters on that side. Major OH, balance your hydrogens using H+. So I have 6 H's there, so I'm going to add 6 H pluses. So major OHE, balance your electrons by adding, balance your charges by adding electrons. And so I need, in order for both sides to equal -1, in this case, I'm going to add 6 electrons to this side. So this is my gaining electrons reduction half reaction. Looking at the next one, I have 2 sulfurs here and 4 sulfurs there. So the first thing I have to do is balance my major species. So I need 4 sulfurs and 4 sulfurs. Major O, balance your oxygens, 6 oxygens and 6 oxygens, so I don't need to add any water. Balance your hydrogens, don't need to balance hydrogens. And so the last is balance my electrons, and I have 4 electrons here, so I need 2 electrons on this side to get that balanced. Now I have 2 half reactions, an oxidation half reaction and a reduction half reaction. I'm going to multiply my half reaction by 3 in order to get my electrons to be balanced. And so that's balanced by 3, and then I have my net reaction. Whew. So here's my net reaction. I now need to add the information underneath and do the stoichiometry. Okay, so we did our major OHE, we came up with that reaction, and then I'm reading in the question, and it says 25 mils of the sodium thiosulfate sample. Now, sodium thiosulfate is sodium and thiosulfate. And so if it's 25 mils, oh, hello. If it's 25 mils of sodium thiosulfate, it means I have 25 mils of sodium ions and 25 mils of thiosulfate ions, and so 25 mils of thiosulfate. So the 25 mils goes underneath the thiosulfate column. So also reading in the question, it wants us to calculate the concentration of the sodium thiosulfate, and it gives us the concentration of the IO3 minuses and the volume of the IO3 minuses. Again, within the compound, but within that compound is a species list, and this is part of that species list, and so I can write it under that column. Okay, so remembering for stoichiometry, there's a dance that we do where we go and find our number of moles of what we know about. So this is number of moles of our IO3 minus. This will be the first thing that we do. So I talk about going down that stream. And then we have to cross the bridge to change the conversation about the other species that we want to answer the question about. And the only way that we can cross the bridge from one species to another or from one conversation to another is we have to use our mole ratio. So number 2, we use our mole ratio, which in this case is a 6-to-1 ratio. Those are the coefficients of the balanced equation. That's going to give us our number of moles of S2O3 2 minus. Then once we have, so the first thing we do is to go down that stream to figure out number of moles. Then we cross the bridge to change the subject into the moles of the other thing. And then we're going to go up into this stream and we are going to answer the question mark. That'll be the third thing that we do. So here's the math. So here's the first thing that we did is we solved for the number of moles of the IO3 minus. This is the same as it was for Chem 20, this stoichiometry. It isn't any different. So we're going to solve for the number of moles of IO3 minus by taking my volume and my concentration. You can see that the liters cancel out and I'm left with millimoles, so 0.67 millimoles. I then, number two, I then multiply that by my mole ratio. My moles of IO3 minuses will cancel out the moles of IO3 minuses, and I just change the subject into 4.04 millimoles of SO3 2 minuses. Now I can solve for the concentration of my SO3 2 minuses by taking those 4.04 millimoles and dividing that by 25 milliliters. The millis cancel out and I'm left with 0.6162 moles per liter. So that's the stoichiometry behind it. I'll do one more. Okay, here's an example that gives us some data. So the question is, what is the concentration of potassium permanganate solution? So this is this purple potassium permanganate solution that I am adding. The table says that this is a titration of 10 mils of 0.05 moles per liter acidified tin 2 chloride. So in this flask, just like we started with in this conversation, I have a bunch of tin 2 plus, it's been acidified, and I'm dropping in this purple potassium permanganate. I would like to know what the concentration is of that potassium permanganate. And I do 3 trials of this self-indicating titrant. And as I add these, I record my initial and my final volumes on my burette. So when you do the subtraction here of these trials, my initial burette reading was 4.3, so almost at the top there. I opened it up. I added my drops. They were colorless as I added them until I got that one excess drop of my permanganate, which means that this then turned this light pink because I had one drop of extra purple within it. And my final burette reading at that point was 22.60. So the difference in that subtraction there is I must have taken out of the burette 18.30 mils and then it changed color. For this trial, I took out 17.30 mils. Here I took out 17.20. Notice I'm adding the 0 because of significant digits here. I'm doing a subtraction of these values. I have 2 decimal places that I'm subtracting, and then, so therefore I should have 2 decimal places in my answer of my subtraction. So 17.30, 17.20, and this one is 17.20 again. Now I have an outlier here. This one is my outlier. This volume is a whole mil different from these other 3. These 3 are nice and close, so I'm going to take those and I'm going to ignore that outlier. The golden rule is it should be within 0.20 mils. Your titrations should be, but really they'll either close or not close is kind of more the point. And so the V average of these is 17.23333 repeating mils for those averages. And so that is how much purple stuff came out. And this is my purple stuff in my balanced equation. So the volume here is 17.23 mils. Now back up. How did I get this balanced reaction? Well, reading in the purple question, what is the concentration of potassium permanganate solution? And here's the stuff that I'm titrating it with. I have to go back to saying, this is a redox reaction. I have a bunch of stuff in my flasks. How do I know what is going to be my oxidizing agent and what is going to be my reducing agent? I have to use my skill about predicting redox reactions. So in the first example I gave you, we used our major OHE skill, and here we're going to use our predicting redox reactions skill. So in order to predict our redox reactions, just a little quick reminder here, we first have to write our species list. So here's my species list: potassium permanganate solution, acidified tin 2 chloride. And then I literally take my data booklet and literally take my finger and put it on the top left-hand corner, and I try to find my strongest oxidizing agent. If you don't use your finger, you will lose your place. It's like little grade 1ers reading, and if they don't use their finger to keep their place in line, then they jump all over that text thing. You'll do the same mistake. So take your finger and put it on the top left-hand corner and try to find your strongest oxidizing agent. And you'll find that that partnership is your strongest oxidizing agent. So you write her down. Then I put my finger on the bottom left-hand corner and I work my way up to try to find my strongest reducing agent. The strongest reducing agent is tin 2+. And once I find it, I write her down. So here's my tin 2+ becoming tin 4+ and an electron. Okay, so then I notice that I have 5 electrons and 2 electrons, so I have to balance my 2 half reactions, and then I write my net. Okay, so once I have my net, I can write the information underneath from the question. The question in the box above the data table tells me my volume of tin 2+ and the concentration of tin 2+. It also, I calculated the volume of the permanganate, and I'd like to know the concentration. So just like we did before, in order to do my stoichiometry, I'm going to first calculate the number of moles of this guy. Then I'm going to use the mole ratio to cross the bridge and change the subject. And then I'm going to go up and calculate the question mark. So the first thing I do is calculate the tin 2+, so the volume and the concentration gives me 0.5 millimoles. Then I'm going to use the mole ratio, so those 0.5 millimoles times 2 permanganates for every 5 tin 2+s leaves me with 0.2 millimoles of permanganate. And then the concentration is going to be those 0.2 millimoles divided by my 17.23 milliliters, and I end up with 0.0116 moles per liter. Now, for those of you that like to do not 1, 2, 3, but it all in one great big line, if you are able to do that, then please do. It doesn't matter at all, as long as a person can find your communication. But a lot of people can't quite follow that logic the whole way, and they often make a mistake somewhere, flip a ratio that they shouldn't flip, get lost in the units, and therefore I break it down into 3 steps. There is no you don't get extra points for doing it in one great big line. So do whatever works for you and get the right answer is the best way to do those things. So if you're doing it in one great big line, I should see these things multiplied, then this thing multiplied, then it divided or timesing by 1/17 in order to get the same answer that I got. Redox titrations.